Hello and welcome to my new series on beyond infinity transfinite numbers. This is going to open your mind to infinity and how infinity isn't just a horizon that we never reach, but it can be a complete mathematical object. And before we get straight into transfinite numbers and how they work, we have to first talk about set theory, and it is important understanding how they work. So this is not the same as my previous video, but this talks about the pitfalls of earlier systems of set theory and how we changed them and what was wrong with them. Okay, let's go. So, the crisis of logic. In the 19th century, we had something called naive set theory. In naive set theory, any property could be made. So, for example, if you wanted to have a set of all cats, then you would create or a set of all colors or something, you have to create it as well. So you just have to create any set that you can basically say anything that fits in a box basically. You can describe it. Moving on. There was a flaw in this sort of definition of this set theory, the naive set theory. And so if you wanted to have a set of all things that don't contain themselves, it's a loophole in the system, and it just creates a logical explosion. So think about it this way: imagine a barber. If a barber shaves people who do not shave themselves, can the barber shave himself? Well, if he does, he can't, because he shaves people who don't shave themselves. And if he doesn't, he must, because he shaves people who doesn't shave themselves. And so logic completely crashes down. There is, however, a mathematical version of this, created by Bertrand Russell, known as the Russell paradox. And Russell proved that if we allow sets to be built without any rules, then we can create nonsense, because if you can't have a set of everything that doesn't contain itself, or a set of all X that doesn't do X, or it just doesn't make sense. It's a logical paradox. And so we get this idea of ex falso quod libet, which translates to from any falsehood anything follows. So if you prove one contradiction is true, then the whole system explodes. And so if you can prove 0 equals 1, then you can probably prove that the moon is made of cheese or something. It just completely discredits the system that they're using. It's known as a logical explosion. And so what is an axiom? So an axiom is basically the foundation or starting rule that we accept true without needing proof. It's the ground floor of logic. Think of it as the rules of chess. You don't prove why a pawn moves forwards. Everyone just agrees to the rule, and then the game starts, and you just play using the rules that have already been put in place. And this led to the safety net, the new set theory that we use today, modern set theory, known as the Frank set theory. which stops paradoxes, and it has a set of 9 axioms which restrict and govern how the sets are allowed to exist. So you want to be able to create a set of all sets that do not contain themselves, for example. And one of these is the axiom of specification. Instead of building sets from thin air, this rule says you can only build a set by filtering elements that already exist. Since there are no set of all sets to start with, Russell's paradox is impossible to build, and the problem of self-containment is solved. And another key one that we're going to look at is the axiom of choice. So the rule, the C in ZFC, says you have an infinite collection of bins. You can reach into every one and pull out exactly one item, even without specific instruction. So again, why this is important later and why it prevents sort of glitches in the math world. But that's it for today, and that's all on the brief history and all the key parts of the previous set theory, naive set theory, and why it came to be Zermelo-Fraenke set theory that we have today.